Hi scholars, Tutor Marvis here again. So in this video I want us to revise radioactivity together, and this is one topic that many students, especially the secondary school, find challenging. So I prepared this note especially for you. I prepared this note specially because of you. So I want you to follow through every bit of it. Alright, so let's start with the background story about radioactivity. Now, before that, please know that radioactivity does not mean the activities of radio. So that's just by the way. In the year 1896, Henry Becquerel noticed that a crystal of uranium salt spontaneously emitted radiation which could penetrate through opaque material to affect a photographic plate. Further experiments showed that the metal uranium and all its compounds possessed the same property. All right? Henry Becquerel now concluded that the uranium atoms were responsible for the emission of this unknown. All right. Number 4, application. Cesium-137 used in medical application and industrial gauges. Then we have PET scans. PET scans, that's another thing we use radioactive isotopes for. PET means positron emission tomography. And this scan uses radioisotopes like fluorine-18 to help visualize metabolic processes in the body. Then we have SPECT scans, single photon emission computed tomography. It utilizes isotopes like technetium-99 to access blood flow and detect abnormalities. Then it can also be used for cancer treatment. Yes, radioactive isotopes can be used for cancer treatment. Isotopes such as iodine-131 are used to treat thyroid cancer. Other isotopes like lutetium-177 target certain types of tumor, that is some growth in the body. Then number 8, pain relief. Radium-223 is used to alleviate bone pain in patients with metastatic cancer. Then number 9, we have radiography. Radioisotopes like cobalt-60 are used in industrial radiography to inspect welds and structural components for integrity. Gauge and measurement. Isotopes such as cesium-137 are used in level gauges to measure the levels of liquids and solids in tanks. Then 11. Radioactive tracers are used in processes such as leak detections in pipelines and monitoring the flow of fluids in industrial processes. 12. Food irradiation. Radioisotopes like cobalt-60 are used to irradiate food to kill bacteria and parasites. To irradiate simply means to expose to large amount of heat. So to kill bacteria and parasites, extending shelf life. Then pest control. Pest control, the sterile insect technique. Alright, SIT. Uses irradiated male insects that are released to mate with wild females, reducing pest populations without chemical pesticides. 14. Uranium-235 and plutonium-239 are used as fuel in nuclear reactors, providing a significant source of energy. 15. Radioisotopes are used in radiation detectors and monitoring devices to ensure safety in an environment where radiation is present. So quickly, let's look at the types of radioactivity. Radioactivity can be grouped into 2 main types based on its origin. Number 1, natural radioactivity. Number 2, artificial or induced radioactivity. So what are natural radioactivity? They occur naturally in elements like uranium, thorium, and radium, and they are found in rocks, soil, cosmic rays, and even living organisms. Examples of natural radioactivity are alpha, beta, and gamma emissions from naturally occurring radioactive isotopes. While in the case of artificial radioactivity, they are human activities. They are produced by human activities such as nuclear reactions in reactors or particle accelerators. How are they created? They are created when stable nuclei are bombarded with particles. It could be neutrons. Examples, we have carbon-14. Carbon-14 is an example of what? Artificial radioactivity. Technetium-99 is also a result of artificial radioactivity. So in a nutshell, natural radioactivity exists without human intervention, while artificial radioactivity is man-made. So let's move to types of natural radioactivity or natural radiation. So there are two types of natural radiation. All right? The first is ionizing radiation, and the second is non-ionizing radiation. As we know, radiation is energy emitted by a source and then travels through a medium such as air until it is absorbed by matter. So based on the energy of the radiated particle, we have two types of radiation. The ionizing one. And ionizing radiation simply means the one that produces sufficient energy. Alright? Ionizing radiation is the radiation with sufficient energy that produces ions in matter at the molecular level upon the interaction. In other words, it can remove tightly bound electrons from the orbit of an atom, causing the atom to become charged or ionized. If the interacting matter is a human body, it can result in significant damage, including damage to DNA and the denaturation of proteins. This is not to say that non-ionizing radiation can't cause injury to humans, but the injury is generally limited to thermal damage, such as burns. One of the most interesting things is that the visible spectrum is essentially the divide between ionizing and non-ionizing radiation. This makes sense clinically when we think of ultraviolet radiation causing skin cancer. So still under types of ionizing radiation, let's look at these 5. You know that under types of natural radiation, we say we have ionizing and non-ionizing. So let's look at the ionizing radiations. We have the alpha particle, we have the beta particle, we have the gamma ray, we have the electron capture, and we have the X-ray. So let's look at alpha particle. Okay, the first thing you need to know about alpha particle is that it is a positively charged particle having mass number of 4 and an atomic number of 2. And the element that has this property is helium. So anywhere you see helium this way, it symbolizes alpha particle. Then 2, since alpha particle is positively charged and fairly heavy, it is deflected slightly towards the negative plate of the electrostatic field. So alpha particle is positively charged, alright, but it is deflected towards the negative plate of the electrostatic field. 3, it has a very low penetrating power and very long wavelengths. Alpha particle has low penetrating power. It cannot travel so fast. That is the meaning. And the barrier, what stops it, is a sheet of paper or an aluminum foil. So it has low penetrating power and it can be stopped or absorbed by a thin sheet of paper or aluminum foil, which is only 0.1 millimeter thick. Then number 5, it has a velocity of about 1/20 of the speed of light. Speed of light is 3 times 10 raised to power 8 meter per second. So 1/20 of this is the velocity of alpha particle. Then number 6, it causes fluorescence in some materials. Example, zinc sulfide. To cause fluorescence means to cause to lighten up. Alright. Then 7, it can be deflected slightly by electric and magnetic field. So these are the things to know about alpha particle. So briefly, before we talk about beta particle, let's talk about alpha decay. So let's talk about alpha decay. Alpha decay. Now when we talk about alpha decay, when an atom, all right, emits, releases or loses an alpha particle, its atomic number becomes reduced by 2 and the mass number by 4. So look at this, for instance. Let's say this is an atom and this atom emits alpha particle, which is helium. So the mass number of the atom will be reduced by 4 and the atomic number will be reduced by 2. So this is how to represent alpha decay. So what you will notice is that the summation of the mass number on the left must be equal to the mass number on the right, and the summation of the atomic number on the left must be equal to what? The atomic number on the right. So let's use uranium as a case study. If uranium disintegrates, we have thorium. So let's say this is uranium and the mass number is 238. The atomic number is 92. So if uranium is emitting or releasing alpha particle, which is helium, thorium will be 238 minus 4. That is 234. And 92 minus 2, that is 90. So this is what we are going to have for alpha decay using uranium and thorium. So let's move to beta particle. Beta particle, there are 2 types of beta particles, all right? The first one is the positive, the second one is the negative. So we have positive beta decay and negative beta decay. How do you represent them? This is positive and this is negative. The positive beta decay is known as positron and the negative beta decay is known as negatron emission. The positive is known as positron emission, the negative is known as negatron emission, all right? So here, let's talk about the negative. It is negatively charged with a mass of 1/1840 units and charges of -1. And how do we represent the negative beta particle? Electron, 0 here, -1 here. The mass number is 0 and the atomic number is -1. Since beta particle, which is the negatron, is negatively charged, it is deflected towards the positive plate of the electrostatic field. And it has a medium penetrating power. The penetrating power is higher than that of alpha particle but lower than that of gamma ray. It has a medium wavelength. It has a wavelength greater than that of gamma ray but lower than that of alpha particle. Alright? And it can be stopped or absorbed by aluminum plate of about 5 millimeter thick. And it has a velocity of 160,000 to 250,000 km per second. Alright? It causes fluorescence in substance just like alpha particle, but it has little effect on zinc sulfide, and it is deflected easily by electric and magnetic field. So this is what you need to know about alpha particle. So let's talk about alpha decay quickly. When an atom emits or loses alpha particle, its atomic number is increased by 1 and the mass number remains constant. So let's use bismuth as example. Mass number 214, atomic number 83. Going to polonium, this is beta. Alright? So 214 minus 0 is the same. So we have 214, but 83 minus 1, that's 84. So the atomic number of this is 84 and the mass number remain unchanged. So this is alpha, this is beta decay. So let's talk about gamma ray. Now, the first thing to know about gamma ray, alright, is that it is an electromagnetic radiation with a charge of 0 and mass of 0. Alright? So, as far as gamma ray is concerned, it has no mass and it has no charge. Since it has no charge, it is unaffected by electrostatic field. Alright? And it has a very high penetrating power. It has the shortest wavelength, even shorter than that of X-ray. It can be absorbed by a large lead block, and it has the velocity of the speed of light. So gamma ray travels by the speed of light. It causes fluorescence in substances like sodium iodide and zinc sulfide, and it cannot be deflected by magnetic or electric field. So in the case of gamma ray, alright, what you are going to notice is that it has a very high penetrating power. Look at this diagram here. If this is alpha particle, once alpha gets here, it cannot survive. It cannot go beyond this barrier. But in the case of beta, it can penetrate this and come to this barrier, but it can't go beyond this barrier. But in the case of gamma, it can go beyond this barrier. So in order of penetrating power, the way we are going to arrange this is alpha is less than beta, less than gamma. Or you say gamma is greater than beta, greater than alpha. Talking about penetrating power. Are we together? So basically, in terms of gamma decay, when an atom loses a gamma ray, its atomic number and mass number remains constant or unchanged. For instance, if we have this element, alright, liberating a gamma ray, the mass number is 0, the atomic number is 0 for gamma, and therefore if you are forming another element, the mass number and the atomic number remains the same. That is the truth about gamma ray. So let's check positron emission. This is also known as beta positive decay. Alright? When an atom emits or loses a positron, its atomic number reduces by 1 and mass number remains unchanged. Then electron capture. It's simply the bombarding atom with electron. When you bombard atom with electron, you have electron capture. Something like this. A minus 0, that is A. This is 1. So this is B minus 1. B minus 1 is B minus 1. Okay. Don't forget that when we talked about beta negative decay, that's negatron, I represented it this way, alright? But when you see this, this is positron, positive beta particle, alright? So the mass number remains unchanged and the atomic number reduces by 1. So in the case of electron capture, we said it simply means when you bombard atom with electrons. That is electron capture. Now what of neutron decay? Neutron is symbolized as this: atomic number 1, atomic number 0, and mass number 1. When an atom emits neutron, its mass number reduces by 1 and the atomic number remains unchanged. So when you have this atom emitting neutron, alright, you have A minus 1 and you have B minus 0. So the mass number is reduced by 1, the atomic number remains unchanged. And one thing you must learn is how to balance nuclear reactions. Always ensure that the mass number on the left is equal to the mass number on the right. Before we move to X-ray, let me give you an example of electron capture. Alright? Now, the whole idea of electron capture is that it's a type of radioactive decay in which an atomic nucleus captures an inner shell electron, usually from the K shell, and converts a proton into a neutron. And this process always results in a decrease in the atomic number of the element while keeping the mass number the same. Let's use beryllium as example. This is 7, this is 4 plus electron. It will give us lithium 7, 3 plus Ve. Alright, so this is the initial nucleus, beryllium 7, and this is an electron captured in the inner shell. Then the final nucleus is lithium, and we have a byproduct, neutrino. So this is a typical example of electron capture. So let's talk about X-rays. X-rays. A lot of times we have come across X-ray, but many of us have not seen X-ray. We don't know who developed X-ray, how it came to be, but we've heard X-ray. So let's journey together briefly as we examine X-ray. X-rays were first discovered by a scientist named W.C. Roentgen in the year 1897. Alright? X-rays are electromagnetic waves like visible light, but with a shorter wavelength. They are produced by allowing fast-moving electrons to hit or bombard metals like tungsten. This movement of electrons is accompanied by the emission of X-ray. So X-rays have high penetrating power, as they can penetrate through flesh, bone, metal foil, wood, and paper. So what are the two types of X-rays we have? We have the hard X-ray and the soft X-ray. Hard X-rays have greater penetrating ability than soft X-ray, and hard X-rays are used for destroying cancerous cells. Soft X-rays pass through the flesh but are absorbed by the dense bones and produce a shadow photograph of the bones. So what are the uses of X-rays? Number 1, it is used for detecting bone fractures. When there's fracture in the bone, you can take X-ray and it will detect where the fracture are taking place. Number 2, identifying dental cavities. 3, diagnosing pneumonia. 4, screening for lung tumors. 5, checking for spinal injuries. 6, spotting dislocated joints. 7, mammography, that's breast cancer screening. 8, radiation therapy for cancer. 9, airport luggage scanning. 10, inspecting welds in pipelines. 11, testing aircraft parts for cracks. 12, examining electronic circuit, PCBs. 13, revealing hidden layers in paintings. 14, detecting art forgeries. 15, studying atomic structures, that's crystallography. 16, analyzing DNA and proteins. 17. Observing black holes. That's X-ray astronomy. 18. Finding metal containment in food or metal contaminants in food. 19. Examining mummies without damage. And 20. Investigating fossils. So these are the uses of X-rays. So let's quickly move to how to detect radiations. Detection of radiations or radiation detectors. What are radiation detectors? Unlike sound that we can hear and odor that we can smell, nuclear reactions cannot be detected through any of our sense organs. Detectors of radiation. Unlike sound that we can hear and odor that we can smell, nuclear reactions cannot be detected through any of our sense organs. So we rely solely on instruments to detect them. So let's look at some of the devices that have been developed over the years for detecting radiation. And the common ones are these. Number one, we have Geiger-Müller counter. The Geiger-Müller counter was developed by Hans Geiger and Walter Müller in 1928. The combination of their names is what brought about Geiger-Müller counter, and it is used for detecting alpha particles, beta particles, and gamma ray. Number two, we have scintillation counter. The scintillation counter was developed by Sir William Crookes in 1903 when he invented the first scintillation screen using zinc sulfide. And they are of two types, the solid detector and liquid detector. A popular solid scintillating detector is the thallium drifted sodium iodide detector for detecting gamma ray, and liquid scintillating detectors are mainly used for detecting beta particles and in some cases alpha particles. The third one, diffusion cloud chamber by Wilson cloud chamber. All right, okay, it's also called Wilson cloud chamber. The diffusion cloud chamber was developed by Alexander Langsdorff Jr. in 1939. It was an improvement on the original cloud chamber, which was invented by Charles Wilson in 1911. The diffusion cloud chamber operates at low temperatures and is used to visualize ionizing radiation tracks. It is used in detecting the actual path followed by alpha and beta particles. Then 4, we have the proportional counter. The proportional counter was developed by Samuel Curran in 1940. It is used for detecting gamma rays only. 5, ionization chamber. The ionization chamber was developed by Wilhelm Röntgen in 1895. It is used for detecting gamma rays. All right. Then we have the nuclear emission and solid state nuclear track, developed by Ernest Rutherford, E.P. Fiester, P.B. Price, R.M. Walker, and C.T.R. Wilson in the early 20th century. They are detectors for autoradiographic images. They detect alpha particle, beta particle, and gamma ray, just like the Geiger-Müller counter. All right. It uses a photographic emulsion to record the tracks of charged nuclear particles, such as alpha particle, fission fragments, or heavy ions. So let's look at the non-ionizing radiation. All of these ones that we have explained are the ionizing radiation. And let's look at the non-ionizing radiation. We don't have much to talk about under this. It is the term given to radiation that has insufficient energy to cause ionization. These kinds of radiation contradict ionizing radiation like X-rays, gamma rays, and alpha particles, which are on the other end of the spectrum and are unstable and reactive. Non-ionizing radiations can produce heat, which is how food is cooked in the microwave oven. Humans and other organisms can see some types of non-ionizing radiation, such as visible light and infrared light. So, we have types of ionizing radiation: ultraviolet radiation, visible light, infrared, microwave, radio waves, very low frequency, that's VLF, extremely low frequency, thermal radiation, and black body radiation. The next thing we are going to be talking about is nuclear energy versus binding energy. So what is nuclear energy? Nuclear energy is the energy released during nuclear reactions, particularly through processes such as fission, fusion, and radioactive decay. So what is binding energy on the other hand? Binding energy is the energy required to disassemble a nucleus into its individual protons and neutrons. So we can see the difference between the two. For nuclear energy, that's the energy released during nuclear reactions. For binding energy is the energy that is required for that reaction to take place, all right? And binding energy is also the measure of the stability of a nucleus. That is, the higher the binding energy, the more stable the nucleus. So let's look at three concepts under nuclear energy. The first, we have nuclear fission. What is nuclear fission? This simply is splitting of heavy nuclei into smaller fragments, along with the release of energy and neutrons. So let's see a case study of nuclear fission. The first, let's use uranium-235. When uranium-235 absorbs a neutron, it can undergo fission, all right? So this is uranium with the molar mass of 235 and atomic number of 92 plus neutron, all right? So since this is splitting, it's going to split into two smaller elements. We have 14456, this is barium, plus krypton, 89 and 36. All right, then plus energy. Then we can also have plutonium. Plutonium can split, Pu 239 94 plus neutron can split to barium and strontium, 56 plus 94 38. Then our neutron becomes 2 here, plus energy. All right, then we can have a third example. Uranium-233 can be used. Uranium-233 with atomic number 92, giving us krypton, all right, 90 38 143 54. Then plus energy. This is 102. So these are examples of the nuclear reactions that has to do with fission. So uranium splitting into two smaller fragments, and plutonium also splitting into two smaller fragments. So the whole concept of nuclear fission is splitting of heavy nuclei into smaller fragments alongside the release of energy and neutrons, as you can see. So let's talk about nuclear fusion. So in the case of fusion, fusion simply is combining light nuclei to form heavier ones, all right? Combining light nuclei to form heavier elements. Light nuclei like hydrogen isotopes to form helium, all right? And in the case of fusion, fusion requires extreme heat or pressure, and it releases 4 times more energy than fission. So let's consider examples of nuclear fusion. So examples of nuclear fusion, since it has to do with combining elements. So let's have hydrogen plus hydrogen, all right, giving us hydrogen plus 1 0 electron. Now this hydrogen with molar mass 2 is known as deuterium. This is hydrogen plus hydrogen giving us deuterium, all right? This is an example of fusion when 2 light nuclei comes together to form, a heavier one. Then we can also have deuterium and tritium. That's hydrogen with molar mass 3, all right? These 2 can form helium. These 2 can form helium plus neutron, all right? So if you check, 2 plus 3 is 5, 4 plus 1 is 5. 1 plus 1 is 2, 2 plus 0 is 2. Like I said in the when we're treating decays, I said the sum of the molar mass on the left must be equal to the sum of the molar mass on the right. And the same is true for the atomic numbers. Then another example of fusion is we can have what we call the triple alpha process, helium fusion. Helium fusion to form carbon-12 is also known as triple alpha process. This, all right, plus, yeah. So 3 helium can fuse to form carbon-12. 3 helium 4 nuclei can fuse together to form carbon-12, just like we are seeing here. So the next one and the last one here is artificial transmutation. What does it mean? It means human-induced conversion of one element into another. That is what artificial transmutation is. When you convert one element to another, when you change one element to another. So let's look at example. Number 1, carbon-14 can be produced when nitrogen-14 absorbs neutron. Like this. This is plus neutron. It can give us carbon-14 plus hydrogen. All right. So 14 plus 1 is 15. 14 plus 1 is 15. 7 plus 0 is 7. 6 plus 1 is 7. Then gold can be transformed into mercury. Gold, Au, 197 and 79 plus neutron can be transformed into mercury, 197, 80 plus electron. Then phosphorus can be created from silicon. Let's have silicon 28, 14 plus neutron can produce phosphorus. So these are all examples of artificial transmutation. Hello, Tutor Malvis here again, and this is going to be the final episode on radioactivity, where we'll be discussing half-life, mean life, and decay law. So, what is half-life of a radioactive element? Half-life often symbolizes or is designated as T-half, alright, is the time taken for a radioactive material to disintegrate or decay. To disintegrate or decay into half of its original mass. Its original mass. So this is the definition of half-life. It is the time taken for a radioactive material to disintegrate or decay into half of its original mass. So mathematically, half-life is given as ln 2 over lambda, and ln to 3 decimal places is 0.693 over lambda. So for UTME student, you will not have the liberty to press ln or log on the calculator given to you. So it's best you just know that it is what? 0.693 over lambda. Now, how did we come about this relationship? From the exponential decay law, we have n into t equals n naught e raised to power minus lambda t. Alright? And when n into t equals n naught over 2, which is half-life, because n naught talk about the initial size or initial quantity of a particular material, then we can say this is n naught over 2 equals n naught e raised to power minus lambda t. Alright? So this gives us half equals e to the power of what? Lambda t half. So we take the natural logarithm of both sides. We have ln 1 over 2 equals lambda t half. So our t half will be what? Ln 2 over lambda. Now, the negative sign, let me just explain why that lambda is carrying negative, though I'm still going to talk about it later, because I will show you how we got this exponential decay law. But the negative sign indicates that the number of radioactive nuclei decreases with time. But here, I've just shown you how we got ln 2 over lambda to be the formula for half-life of a radioactive element. So this is the formula we'll be using, and in this formula our lambda, which is this, is known as the decay constant. Alright, and if you make lambda the subject of formula, you are going to have 0.693 all over what? The half-life. So as half-life equals 0.693 over lambda, lambda is also 0.693 over half-life. So let's move to mean life. What is mean life? Mean life is simply the reciprocal or inverse of decay constant. And we know that the decay constant is what? Lambda. So now mean life is represented by this symbol, tau. Looks like T. This is tau equals 1 over lambda. And if it is 1 over lambda, it shows that it will be what? Half-life over 0.693. So in conclusion, we have half-life to be 0.693 over lambda, and we have lambda to be 0.693 over half-life, and we have mean life to be 1 over lambda, which is the same thing as half-life over 0.693. So depending on what the question requires of you, you can deploy any of these formula. So let's talk about the radioactive decay law. Radioactive decay law. What does it state? It states that the rate at which a radioactive substance decays is directly proportional to the amount of the substance present. All right. So the radioactive decay law states that the rate at which a radioactive substance decays is directly proportional to the amount of substance present. So mathematically, we have dn dt is proportional to n, and our dn dt equals minus lambda n, where lambda is the decay constant. So if at time t naught, the undecayed nuclei is n naught, we are going to have dn over n naught equals minus lambda dt. If we integrate both sides, we have dn over n naught equals integral of minus lambda dt, and this will give us n into t equals n naught e raised to power lambda t. So what is the significance of this expression? This is the mathematical representation of the decay law. So what does NT means? It means the number of undecayed nuclei at time t, or you can call it the number of radioactive atoms remaining at time t. All right. So what of n naught? N naught is the initial number of radioactive atoms, or you can call it the initial count rate, or you can call it initial mass, and so on and so forth. Our lambda is the decay constant that is specific to the particular isotope, and t, small t, is time elapsed. All right, let's proceed from this formula, all right, and make lambda the subject of the formula. How do we go about that? So this is what we have. n into t equals n naught e to the power of lambda t. Now, to make lambda the sort of formula here, divide both sides by n naught. If we do that, we are going to have this n naught e to the power of negative lambda t over n naught, and nt over n naught will be equals to e to the power of negative lambda t. So what do we do from here? Take the natural logarithm of both sides. Alright, equals ln e to the power of this. And by so doing, you are left with ln n into t over n naught equals minus lambda t. Then divide both sides by negative 1. You have minus ln n into t n naught equals lambda t. Then divide both sides by t so that you can isolate lambda. So lambda will be 1 minus 1 over t ln n into t all over n naught. So this is the formula for the decay constant according to the decay law. And in this formula, you have your parameters defined already. Nt to be the number of undecayed nuclei or the remaining nuclei at time t. N naught is the initial count rate or the initial number of nuclei or the initial radioactive atoms. And t is the time taken or time elapsed. Now, this formula is suitable if you have access to a scientific calculator. But for the sake of UTME, where you will not be allowed to use log, ln, whatever. So, how do you calculate the remaining quantity of a radioactive material? If you want to calculate remaining quantity of a radioactive material, you simply use n equals n naught multiplied by half to the power of n. So this relationship you use, this n here is the remaining quantity after n half-life. This capital letter n is the remaining quantity. This n naught is the initial quantity, and this small letter n is the number of half-lives. And this small letter n is defined as t over t half, that is time elapsed over half-life. So it shows that this formula can be rewritten as something like this, t half. Are we together now? So don't forget, this n here means remaining quantity after n half-life, and this n naught is the initial count rate or initial quantity or initial mass, and n is the number of half-lives. What if they ask you to calculate the fraction that has decayed? Fraction of a material that has decayed, fraction decayed, is calculated as 1 minus half to the power of n. 1 minus half to the power of n. This is how you calculate fraction that has decayed. So basically, I believe that this is all you need to solve any calculation whatsoever as far as radioactivity is concerned. And I'm going to demonstrate this in the next chapter of this video by solving 13 questions from the past question. Stay tuned. Alright, so let's take these practice questions together. Number 1, a radioactive substance with a half-life of 5 seconds has a decay constant of dash. Alright, so we are given the half-life to be 5 seconds. And they ask us for the decay constant, lambda. And you know that lambda equals 0.693 over half-life, which is 5. So simply, you press 0.693 divided by 5. You're going to have 0.1386. 0.1386. So to 3 decimal places, you have 0.139. And that makes option D the correct answer. Question 2. The half-life of a radioactive substance is 10 minutes. What is its decay constant? So the decay constant is lambda, that is 0.693 divided by 10. And that should give us 0.0693 per minute. Option A. Then question 3. We have the mean life, tau, of a radioactive substance is 20 seconds. What is its half-life? Now you and I know that mean life is the reciprocal of decay constant. So that makes this to become T half over 0.693. So we have been given the mean life to be 20, and this is our half-life unknown over 0.693. So half-life will be 20 multiplied by 0.693. So just say 20 multiplied by 0.693. And that gives us 13.86 seconds. That makes option B the correct answer. Let's look at question 4. If the decay constant, lambda, of a radioactive substance is 0.002, what is its mean life? You know that mean life is 1 over lambda. So that is 1 divided by 0.002. Alright? So you just say 1 divided by 0.002. And that gives us 500. 1 divided by 0.002, that is 5. Question 5. A substance has half-life of 3 minutes. After 6 minutes, the count rate was observed to be 400. What was its count rate at 0 time? Okay, so let's analyze this question together. The initial count rate, initial count rate is what we don't know. That's what they said. What was its count rate at 0 time? So that's the initial count rate. We don't know. So what is the count rate? Count rate after 6 minutes. That is our N is 400. All right. Then a substance has half-life of, so we are given half-life of 3 minutes. Then we are given time elapsed 6 minutes. So the formula remains N equals N naught multiplied by half to the power of N. Don't forget. So what will our small n be? That's number of half-life. It will be T, small letter t over half-life. So that will be 6 over 3, and that is 2. So coming here, I'm going to just substitute. What is our n? 400. N naught is unknown. And this is half to the power of 2. So we have 400 equals n naught multiplied by 1 over 4. So n naught equals 400 multiplied by 4. And that is 1,600. So the answer to this question is A. So what you just need to endeavor to do is remember this formula. It is very, very vital. Let's solve question 6 together. 4 grams of a radioactive material of half-life 10 days is spilled on a laboratory floor. How long would it take to disintegrate 3.5 grams of the material? Okay. Now, we have 4 grams. That's the initial mass. 4 grams of a radioactive material. The initial mass is 4 grams. All right. and half-life is 10 days. T half, write your 10 days. Then is spilled on the laboratory floor. How long would it take to disintegrate? So we don't know the time elapsed. Small letter t is unknown. To disintegrate to 3.5 gram, all right, of the material. So the mass disintegrated is 3.5. So we need to know mass remaining. We need to know mass remaining because we already have the initial mass to be 4 gram. So mass remaining is our N, and that will be 4 minus 3.5. So that is what? 0.5. So our N is 0.5 and our N naught, the initial mass or the initial quantity, is 4 gram. All right. So it's like we have everything we need. So our formula remains N equals N naught half to the power of N. So here, before we can find our T, let's find N. So we have N here, that's 0.5, N naught, that is 4 gram, and this is half to the power of N. So this 0.5 divided by 4 equals half to the power of N. So if we use reciprocal law of indices, this can be 4 over 0.5 equals 2 to the power of N. So you simply press 4 divided by 0.5. What do you have? You have 8. So 8 equals to 2 raised to the power N, 2 raised to the power 3 equals to 2 raised to the power N, and N equals to 3. Now if N equals to 3, don't forget that N is T over half-life, and they want us to find T. So our T will be equals to N times half-life, and our N is 3. Half-life given to us is 10. 3 times 10, that is 30. So the answer is 30 days, and that makes option C the correct answer. Alright, let's solve question 7. The count rate of a radioactive material is 800 counts per minute. 800 count per minute. Let's write that. The count rate. So that will be the initial count rate. 800. Okay. If the half-life of the material is 4 days, half-life 4, what will be the count rate? N unknown. 16 days after, that is small t, time elapsed 16 days. So we need our N, all right? The formula remains N equals N naught half to the power of N. And you already know that N is T over half-life. So what is T? 16, half-life 4. So our N is 4. So by substitution, N here is unknown. We have N naught, that is 800 multiplied by half to the power of 4. So this is 800 times 1 over 16. So you simply press 800 divided by 16. We have 50. So the answer to this question is 50 counts per minute. And that makes option C the correct answer. Number 8. A piece of radioactive material contains 1,000 atoms. So the initial quantity is 1,000. So you will see that these questions are following the same pattern. You just need to know your formula and how to apply it. So the initial quantity is 1,000. If its half-life, T half, is 20 seconds, the time taken for 125 atoms to remain is, so we don't know the time taken, all right? And they told you that remaining quantity, the time taken for 125 atoms to remain is dash. So remaining quantity, which is our N, is 125. So N naught is always the initial quantity, while the remaining quantity is N, all right? So they want us to find small t. So our formula remains n equals n naught into half to the power of n. Alright? So we need to find our small n before we can get our t. So our n here is 125. Our n naught is 1000 into half raised power n. So this is 125 over 1000 equals to half raised power n. So I can swap this to become 1000 over 125 equals to 2 raised to power n. And 1000 over 125 is 8. That's 1000 divided by 125. That is 8. So 8 is the same thing as 2 to the power of 3, which is 2 to the power of n. N equals to 3. And if n equals to 3, don't forget that n equals t over t half. So the t they require us to find will now be n times half-life. Our n is 3, and the half-life given in the question is 20. 3 times 20, that is 60 seconds. That makes option C. Question 9. 100 grams of radioactive mass has a half-life of 5 days. Calculate the mass remaining after 15 days. Okay, so the initial mass, which is n naught, is 100 grams, and the half-life given to us is 5 days. Calculate the mass remaining, n unknown, after 15 days. That is t. 15 days. Okay, our formula remains n equals n naught into f into half to the power of n, and our n is t over t half. So what is t? 15 days. What is t half? 5 days. So our n is 3. So let's come back here. We have n equals to 100 multiplied by half to the power of 3. So this is 100 times 1 over 8. So this is saying 100 divided by 8. What's 100 divided by 8? 100 divided by 8. You have 12.5. And that makes option C the correct answer. Then question 10. In 24 days, a radioactive isotope decreases in mass from 64 grams to 2 grams. So the time taken is 24 days. The initial mass is 64 grams. The mass remaining is 2 grams. What is the half-life of the radioactive material? So T half, unknown. So to find the half-life, we need to first find small n. That's the number of half-life. So we have our formula, n equals n naught into half to the power of n. So this n is 2. This is 64 into half to the power of n. So we have 64 over 2 equals 2 to the power of n. 64 divided by 2, that's 32. And 32 can be written as 2 raised to power 5. Then this is 2 raised to power n. Therefore, our n is 5. And don't forget that n is time taken over half-life. So they ask us to look for the half-life. So that will be t, which is time taken over n. The t given to us is 24, and the n we got is 5. So 24 divided by 5, that will be 24 divided by 5. Give us 4.8. So the answer to this question is option D, 4.8 grams. Number 11. In 30 days, a radioactive isotope decreased in mass from 80 grams to 5 grams. The same format. In 30 days, the initial mass was 8 grams, and what is remaining now is 5 grams. What is the half-life? Alright, so n equals n naught half raised to power n. So 5 equals 80 half raised to power n. So we have 80 over 5 equals 2 to the power of n. 80 divided by 5 is 16. So that would be 2 raised to the power 4 equals to 2 raised to the power n equals to 4. So we have to find the half-life, and half-life will be T over n, and that will be 30 divided by 4. Our half-life is 7.5. 30 divided by 4, that's 7.5, and that makes option C the correct answer. Okay, so question 12. After 3 half-lives, the fraction of a radioactive material that has decayed is dash. Now remember that I gave you the formula for fraction decay. Fraction decay equals 1 minus half to the power of n. So here our n is 3, number of half-lives, and so our fraction decay will be 1 minus half to the power of 3. That will be 1 minus 2 to the power of 3 is 8, so that's 1 minus 1 over 8, and that will give us 7 over 8. So the answer to this question is option D, 7 over 8. Anytime you are given question on fraction decay, this is what to do. You just substitute the half-life given to you here. So the last question, question 13. The half-life of a radioactive material is 6 hours. So we have T half to be 6 hours. What quantity of 1 kg? So the initial quantity is 1 kg. What quantity of 1 kg of the material would decay in 24 hours? Before we can know what quantity will decay, we need to first find the quantity remaining. Alright, that's n, we don't know. And here they gave us 6 hours. That's our half-life. Then they said what quantity would decay in 24 hours. That's time elapsed, 24 hours. So our formula remains n equals n naught into half to the power of n. So our n, don't forget, is T over half-life. That is 24 over 6, and that is 4. Now if that is 4, our n will be n naught is 1 into half to the power of 4. Half to the power of 4 is 1 over 2 to the power of 4, and that is 1 over 16. So how do we know the mass that has decayed? Mass decay will be the initial mass, which is 1, minus what is remaining. So 1 minus 1 over 16, that will give us 15 over 16 kilogram. And that makes option A the correct answer. Thank you for watching. Don't forget to subscribe to this channel if you are coming across it for the first time. Kindly share to your learned colleagues. Drop your comment and your question. I hope to read from you soon.